Let's dive into the database per service pattern. This pattern aims to achieve loose coupling between microservices by providing each service with its own dedicated database. This approach enhances service independence, scalability, and data encapsulation. Conceptually, each microservice manages its own private database, accessible only by that service. This enforces clear boundaries and promotes the single responsibility principle. Key aspects of this pattern include data isolation. Each service's data is isolated, reducing dependencies between services. Technology flexibility. Services can utilize different database technologies tailored to their specific needs. Independent scaling. Databases can be scaled independently based on the requirements of each service. Simplified development. Developers can concentrate on a single service and its data model without worrying about impacts on other services. However, as with any design pattern, challenges exist. The first challenge is data duplication. Redundant data across services can lead to consistency issues. Next, we encounter complex cross-service queries. Joining data from multiple services becomes difficult and may require additional patterns, such as API composition. Another challenge is transaction management. As you decouple your data into different data stores, you lose the inherent data integrity provided by traditional RDBMS. Ensuring data consistency across services without distributed transactions can be challenging. Additionally, there is increased operational complexity. Managing multiple databases can be more challenging than overseeing a single shared database. We also need to be aware of common mistakes to avoid. For instance, overusing the pattern. Applying this pattern unnecessarily to small services or tightly coupled domains can lead to increased complexity without significant benefits. Next is neglecting data migration. Failing to plan for data migration when splitting a monolithic database into separate service databases can create issues. Lastly, ignoring eventual consistency. Not designing systems to handle eventual consistency between services can result in data inconsistencies. Now, let's explore how this pattern translates into real-world applications. In the previous video, we adapted a monolithic e-commerce platform into a microservices architecture. Today, we'll build on that foundation by applying the database per service pattern. Our current architecture consists of 4 main services: the product service, inventory service, shopping cart service, and order tracking service. Before implementing the database per service pattern, it's crucial to have a solid understanding of both your business processes and your data. Simply put, if you don't have a good handle on your business processes, you won't be able to define clear boundaries between the microservices. And if you don't govern your data, if you don't know its sources and who uses it, it's just unwise to apply this pattern. Doing so will likely exacerbate existing issues. To proceed effectively, the first step is to initiate a data governance program. I encourage you to check out the introductory videos I published earlier on this topic. Now, assuming you have a good handle on your data, you should be able to clearly identify which service is responsible for creating data and which services consume it. In this example, the product service owns the product and category tables. The inventory service owns the inventory and location tables. The shopping cart service owns the cart and cart items tables. And the order tracking service owns the order, order item, and order status tables. With this understanding, you can begin splitting your database schema into smaller, specialized databases that will be managed independently by each service. Now, let's examine how we can split our initial database schema to ensure each microservice owns and manages its data exclusively. In this design, I want to emphasize that services become loosely coupled, without any shared databases. This architecture allows for significant flexibility in database technology choices, tailored to each service's specific requirements. For instance, one service might leverage MongoDB or DynamoDB for its NoSQL capabilities. Pushing this decoupling even further, we could host services across different cloud providers, utilizing Azure Cosmos DB or Google Cloud Data Store for NoSQL needs. Granted, this will be expansive, but the crucial principle to understand with this pattern is that data access occurs solely through each service's API, maintaining strong encapsulation. This pattern not only enhances scalability and flexibility, but it also allows teams to optimize each service's data layer independently. Okay, that's all for today. Hit the like button. Subscribe And I'll see you soon.